In our previous session, we had discussed about the airfoil design and we had obtained a graph after the analysis. So let us start off with airfoil analysis graph. Before we move on to the airfoil analysis graph, let me show you how to do the airfoil designing in the software Xfl5. So once we open Xfl5 software, we get this page. Click on File on the top left corner, select Direct Foil Design. Click on Foil, select NACA foils. Our 4-digit NACA foil is 2412 and the number of panels that we will be needing is 150. Click on OK. So this is our airfoil. Here under style you can select points, style, width and color. Let us increase the width and change the color to white. Click on OK. So now let us do the analysis. File, Xfoil Direct Analysis. So this is the graph. Click on Analysis, Batch Analysis, Current foil only. Alpha minimum will be minus 10 degree, maximum 20. Click on Analysis and wait. It's an iterative method which will be done for each and every Reynolds number. Yes, and it's done. Close. So this is the graph that we will be getting. Now let us look into each and every graph. The first thing is CL versus CD graph. The lift to drag ratio is used to express the relation between lift and drag and is determined by dividing the lift coefficient by the drag coefficient, that is CL by CD. If lift decreases in increase in drag, then it means that it will soon stall. Maximum endurance, maximum climb angle for jet powered and maximum range for propeller powered occurs L by D max, that is lift to drag maximum. If the airplane is operated in a steady flight at lift to drag maximum, the total drag will be minimum. The change in angle of attack will reduce the lift to drag maximum, which in turn reduces the lift to drag ratio and increases the total drag of the aircraft. From the graph, we can analyze that there's a good amount of lift produced from minimum drag. As the drag increases, there is sufficient lift, but as drag increases even further, the airfoil will lead to stalling. So the CL max is 1.132 and CD minimum is 0.088. The relation between the angle of attack and the lift coefficient is the most important fundamental to the aircraft design. Increase in angle of attack increases lift up to critical angle called the stall of an aircraft. So here we have a normal flight and then the stall flight. The result that we have got for CL versus alpha is this, which shows there's good amount of lift for less angle of attack. There is 0.34 amount of lift for 0 angle of attack. At 13 degree angle of attack, the lift produced is 1.34. At 15 degree angle of attack, the stall takes place. So after stall, there's a slight increase in lift of the aircraft, which is caused due to inclination effect of the aircraft, which referred to as the fake lift, as once the aircraft is in complete stall, there is no lift or there is no true lift produced after that. Now we have the CM versus alpha curve. Pitching moment coefficient CM changes as the function of angle of attack. The point where CM is 0 is called the trim point. Pitching moment coefficient has to decrease in order to create a negative pitching moment. As long as the pitching moment coefficient slope is negative, the flight will be stable. So there are three types of stability, that is statically stable, statically unstable, and statically neutrally stable. If the aircraft nose is down, then the pitching moment coefficient decreases, that is called stable. If the aircraft nose is up, pitching moment coefficient increases, that is called unstable. And if the aircraft is level, then the pitching moment coefficient is neutral. Trim of an aircraft when the pitching moment coefficient is 0 is to adjust the aerodynamic forces to maintain the set altitude without any control inputs. The Cm versus alpha curve that we have got as a result is shown in the graph here. It indicates that it has a negative slope indicating a stable flight. As alpha increases, the stability also decreases but again increases later. Now we have the CL versus XTR top curve, the relationship between the coefficient of lift top surface of the airfoil. It indicates the lift coefficient obtained at different sections of airfoil in the presence of skin friction drag. It describes how lift is distributed on the top surface of the airfoil at different sections of the wing. The result that we have got for CL versus the top surface of the airfoil is shown in the graph here. The relationship in coefficient of lift to the top surface of the airfoil, it indicates the lift coefficient obtained at different sections of the airfoil in presence of a skin friction drag. Now we have the CLCD versus alpha. The efficiency of the wing at different angle of attack is determined by this graph. Maximum ratio of lift to drag coefficient at maximum angle of attack decides the best performance of the wing. High number of CLCD ratio is good. Having a high number across a wide range of angle of attack is also good. So the CLCD versus alpha curve that we have got is shown in the graph here. The peak performance occurs from the 5 degree to 8 degree angle of attack. So if we are flying an aircraft with an angle of attack greater than 8 degree, then it will be insufficient. The rate is declining from 7 degree angle of attack, which means the wing will stall and the aircraft will eventually crash. Analysis result for selected Reynolds number. Select the highlighted box on the top right corner shown. When we select the different Reynolds number, we will get the graphs for a particular Reynolds number. By double-clicking on the graph, we can change its parameter to whatever variables that we want on the X and Y axis. And then click on OK. For pressure distribution result, click on the OP point view highlighted on the right image. We will get the direct foil analysis. Click Analysis, Define Analysis, where we have Analysis Type 1, Reynolds number 400,000. Click OK. On the right side, select the angle of attack and select Analyze. The pressure distribution result for 0 angle of attack. By clicking on the highlighted drop-down box, the pressure distribution can be seen for different angle of attack. Pressure distribution results changes for each and every angle of attack. As the airflow velocity increases along the surface of the wing, the pressure along the surface of the wing decreases. Similarly, an increase in angle of attack will decrease the separation between the airfoil's upper and the lower section's coefficient of pressure. In the same way that an aeroplane gets more lift as it increases its angle of attack, the NACA 2412 airfoil receives drastically more pressure loss as the angle of attack increases, producing a strong lifting force. So the pressure differential created between the upper and the lower surface of the wing lifts the wing upward in the direction of a lowered pressure. This lifting force is known as the induced lift. Let us see how to read the pressure distribution curve. The upper surface has a lower pressure plotted higher as usual than the lower surface. Lower surface sometimes carries a positive pressure, but at times many design condition is usually pulling the wing downward. In this case, some suction that causes a negative coefficient of pressure, downward force on the lower surface is present near the midcord. Pressure recovery is a region of a pressure distribution where the pressure increases from its minimum value to a value at the trailing edge. This area is also known as the region of adverse pressure gradient. As discussed in the other sessions, the adverse pressure gradient is associated with boundary layer transition and possibly separation if the gradient is too severe. The trailing edge pressure at the trailing edge related to the airfoil thickness and the shape near the trailing edge. For thick airfoils, the pressure here is slightly positive. The velocity is a bit less than the free stream velocity. For infinitely thin sections, coefficient of pressure is 0 at the trailing edge. Large positive values of coefficient of pressure at trailing edge implies more severe adverse pressure gradient. When it comes to stagnation point, it occurs near the leading edge. It is placed where the velocity is 0. Note that in incompressible flow, coefficient of pressure is equals to 0 at this point. Hopefully, you would have understood the designing and analysis of an airfoil. Let us move on to the wing design in the next session. Thank you.